Alright, this video is about plotting the DFT. To begin, I want to remind you that the DFT is related to the discrete time Fourier transform, the DTFT, by this sampling relationship described here. So what we have is that the kth bin, frequency bin, in the DFT is equal to a sample of the DTFT at frequency k divided by n. This is true for an n-point DFT, and also don't forget that we're making the assumption that the length of the signal x, whose discrete time Fourier transform is capital X of f, has length, so x of n has length L, which is less than or equal to n, the length of the transform. So that's a condition for this equality to hold. So to understand how to make a plot of the DFT, a proper plot, what we need to do is think about this relationship between frequency bins and frequency, normalized frequency, f. And to do this, I'm going to draw some lines, some frequency lines. But before we do that, let's just remind ourselves of what's going on here. Let's suppose I have minus 1/2. I'm going to draw the frequency axis 0, 1/2, and 1. And let's take a DTFT that's just a triangle, again just for illustrative purposes, and so on. I won't bother drawing the rest of this. You know that the DTFT is a periodic function. So what I've just drawn is x of f. And what this relationship tells us is that the DTFT, or the DFT rather, is samples of this function across this interval between 0 and 1. So these vertical lines that I've drawn, these stems, are the DFT. The trouble is that we normally want to think of we want, when we make a picture, we want negative frequencies to appear on the left, positive frequencies to appear on the right. But when the DFT calculates a transform, the positive frequencies are on the left and the negative frequencies are on the right. And so what we need to do is figure out how to do the proper indexing of both the vector of DFT samples that are returned and also how to construct a properly scaled frequency vector. So to study this problem, what I'd like to do is, again, let's take a look at an axis. And in fact, we're going to look at two axes. On the top one, I'm going to have two sets of numbers. One is going to be our frequency bin index, which is k. And remember, that goes between 0 and n minus 1. And on the bottom, we have frequencies that go from 0 to 1. I'm going to take and do this exercise for two different cases. Let's start with the n even case, and then we'll take n odd next. So remember that the relationship between frequency and bin index k is given by this formula. So bin 1 corresponds to frequency 1 over n. 0 corresponds to 0, 1 corresponds to 1 over n. Bin 2, when k is 2, frequency f is going to be 2 over n, and so on. Because capital N is an even number, when we get to bin n over 2, that's going to correspond to frequency 1/2. The frequency just prior to that, or the bin just prior to that, is going to be n over 2 minus 1. And so on, all the way up to bin capital N minus 1, which corresponds to the frequency n minus 1 over n. We don't actually get a frequency sample at frequency 1, but we know that frequency 1 is equal to frequency 0 in an aliased sense. So if we wanted to produce a sample of the DTFT at frequency 1, we could just take the DC sample and duplicate it and place it over here. All right. What we want to do now, so we can see the relationship between these bin indexes and their corresponding frequencies. And what we want to do is make a properly scaled frequency axis with 0 in the middle and positive frequencies to the right and negative frequencies to the left. So we know that these frequencies right here, everything, all of these frequencies are our negative frequencies, and these over here on the left are our positive frequencies. So what I'm going to do is I'm going to call these bin indexes over here, I'm going to call those k with a negative superscript, and all of these bins over here k with a positive superscript. And we're going to generate our frequencies by taking our frequency vector by taking these frequencies that belong on the negative side and bringing them over here. But in the process, what we need to do is subtract. Notice that these are all between 1/2 and 1, so we need to use the aliasing property of frequencies and subtract 1 as we bring these down over here. The way that we're going to do that is all of these frequencies will be, the way we'll generate those is we'll take k negative divided by n, subtract 1. So k negative over n gives us frequencies between 1/2 and 1, and then we'll subtract 1, that's the aliasing. And then the frequencies over here, this will be k positive divided by n, and we don't have to do anything to these frequencies because they're already scaled between 0 and 1/2. So that's what happens in the even case. And in the odd case, it's a lot the same. So here's our axis. We'll put 0 on the left. Again, we have frequency bin on the top and frequency on the bottom. Here is the frequency 1. Bin n minus 1 comes just below that, and frequency n minus 1 over n comes just below that. The difference between the even and the odd case occurs down near frequency 1/2, and we have a bin index n plus 1 over 2 that's just a little bit above frequency 1/2, and we have frequency or bin index n minus 1 over 2 that's just a little bit below 1/2. So again, what we're going to do to construct our frequency vector is we're going to take all of these frequencies here, those are our negative frequencies. We'll call all of these corresponding bins, we'll call that k negative, and we'll call all of these up here k positive. And then to construct frequencies between minus 1/2 and 1/2 with the 0 bin in the center is we'll take and k negative divided by n, that converts to frequency, and then subtract 1, and then of course we'll have k positive divided by n for our positive frequencies. So that will generate frequencies here between 0 and 1/2, and then we'll also have frequencies over here on the negative side. We're going to reduce all of this to code in just a few minutes, but before we do that, I want to look again at these cases and figure out how to unscramble our frequency samples as well. So let's set that aside for just a minute and start thinking about how we would write a MATLAB function to exploit these ideas that we've talked about so far. So let's think about writing a function in MATLAB. And let's suppose this function receives an input x, a length n, and a sampling rate fs. So inside what we're going to do is we'll say capital X is equal to the FFT of x, and we'll make that an endpoint transform. So this is where the DFT is computed, and it's an endpoint DFT. Then the next thing that we'll do is we'll say if n modulo 2 is equal to 0, this is the even case, then let's define this variable called k middle. And for the even case, we'll set that to n over 2. Otherwise, we'll say k middle is equal to n plus 1 over 2. So we have these two cases, even and odd. And then we'll end with that. We'll finish that. Okay, so let's go back and think about how to use this k-mid, because now what we need to do is write a MATLAB, is create a frequency vector. So let's go back and think about what we need to do this. Let's in the even case, we've defined this thing called n over 2, and we know that our negative bin indexes go from n over 2 to n minus 1, and our positive indexes go from index 0 up to n over 2 minus 1. So let's write that down. K positive goes from 0 to k mid minus 1, and k negative goes from k mid up to n minus 1. So we're using the colon operator in MATLAB to generate sequential lists of indexes. Let's check to make sure that that's going to work also for the case when n is odd. So again, we defined k-mid in the odd case to be n plus 1 over 2. So that's this number. So k negative goes from n plus 1 over 2 up to n minus 1, and then k positive goes from 0 up to k mid minus 1. So it looks like this will work for both cases. Next, we can declare our frequency, our normalized frequency vector. We're going to put the negative frequencies on the left. So I'll say k negative divided by n, and then we have to alias, so we'll subtract 1. And then we'll put the k positive frequency bin indexes divided by n over here, no aliasing needed. We can also create a non-normalized frequency vector that accounts for the sampling rate by taking our normalized frequencies and just multiplying by the sampling rate. Notice that this vector contains frequencies that lie in between minus 1/2 and 1/2, as we know they should. And so this list of capital F frequencies lies between minus fs over 2 and fs over 2. All right. The last thing we need to do is think about doing an FFT shift on this capital X vector. We're not going to use the built-in MATLAB function, so instead let's think about what's needed here. Again, we need to swap the positive and negative frequency parts of the transform. So once again, what we need to do is take, in the even case, the k negative indexes and put those on the left, and put the k positive indexes on the right. What we're essentially doing is taking the negative samples over here, and we're swapping those with the positive frequency samples so that the negatives appear on the left, positives on the right. So here's the positives, Here's the negatives. So we'll do that in MATLAB by saying k negative, comma, k positive. And we would be done, except that MATLAB uses ones-based indexing instead of zero-based indexing as we've used here. Notice that k positive starts at index 0 and ends, and our bin indexes end at n-1. So we're just going to form this vector with the negative frequencies on the left, positive frequencies on the right, and we're going to just add 1 to that so that now MATLAB will be happy that we are using indexes between 1 and n instead of between 0 and n-1. Now the last step is just to make a plot of capital F, and we'll say maybe do a plot in dB, so 20 times log base 10 of the absolute value of our x vector, our transform. And so that's pretty much an outline of what this function needs to look like. So let's jump into MATLAB and try this out. Okay, so I'm going to create a signal x that maybe it's a complex exponential, and let's take, say, bin 27 out of 64, and we'll now we'll take 64 samples. So what does this look like? We'll say plot real x, and let's also plot the imaginary plot part. All right, there it is. This is a complex exponential. You're now looking at the real and imaginary parts of it. It's got a frequency of 27/64. That's what it looks like. Let's take a look at its Fourier transform by calling a function. I've already written the function. It's essentially the same code that we've already looked at. I have an input signal x. I choose a number of points in the transform, and I have an input sampling rate. The first thing I do is calculate the transform. I tell the FFT function I want an n-point transform. Then I check to see if n is even or odd. Define the positive frequency bins and the negative frequency bins, just like we talked about. Create a normalized frequency vector with a little bit of aliasing on the negative frequencies, as you see here. This is not dividing by n-1, it's dividing by n, and then taking those frequencies and subtracting 1. That's the aliasing step. Then we multiply by the sampling rate to construct a vector of frequencies in hertz. Here we're swapping the two halves of the transform so that negative frequencies are on the left, positive frequencies on the right, adding 1 to make MATLAB happy, and the rest of this is just plotting code. So let's take a look and see what that would look like if we make this plot. So I'll call my function plot spectrum x. I'll say 64 and fs. Well, I don't have an fs. I'll just say it's frequency of 1. So over here on the right, what we see is that we have all of our energy in the Fourier domain concentrated into one frequency bin. If we look at 27 divided by 64, that's the frequency 0.4219, and it looks like all of our energy is concentrated in that one frequency bin, as we would expect. Notice that when I called this function, I let n be equal, this is the value of n, 64, and n and x was a 64-point sequence. Let's see what would happen if I change this to a much bigger number, 1024. That's a power of 2. So I'm still passing in the same data x in this case, but I'm sampling the Fourier transform of that sequence at 1,024 points. So I'm going to have the same function. In fact, this function that we're looking at here on the right, these points, in fact, let's go in here and do this before we go any further. Let's do this. And I'm going to go back to 64. And so you can see the points that are being plotted. There are 64 points across here. And we're going to, if we increase the number of points that we're plotting, we're going to generate more samples in the same interval. So what I want you to think about here is that these samples that we're looking at right now are samples of a function. It's a continuous function of frequency f. And it just so happens that those samples, I get one large sample, which is has an amplitude of 64 because it's a 64-point transform, and all of my energy is concentrated in that one frequency bin. But now we're about to generate more samples of the same function. So this is one set of samples. This is 64 samples of that function. And now here are more samples of that function. I'm going to go in and take off the line type because it clutters up the view. Here are 1,024 samples of that function. Now, you can see that, or I hope you can appreciate that the function itself has not changed. What has changed is that we have taken, in this case, more samples of the same function. If I go back in now, let's try this. Let's change the line to a red line type, and I'll do that, and I'm going to say hold on. Let's see. Maybe this is how I do it. I can't remember how to do this. Bear with me. Okay. So now you can see both cases on one plot. When we took only 64 samples of that function, we were lucky because our samples fell, or maybe unlucky. Our samples fell right on the zero crossings of the underlying function. When we sample on a more fine grid, we can actually visualize the underlying function better. Now, we haven't changed the resolution. Let's go back to X, and instead of doing 64 samples, let's do 1,024 samples of the same sequence. And I'm going to say hold on. And now let's calculate the spectrum again. But now we're going to do a 1,024-point transform. And let's zoom in and take a look at what we have here. We'll zoom in close to the situation, or into the frequency that we're looking at. Notice that the amplitude here goes up to 1,024. But what's happened now is that we've actually changed the shape of the function. To see this, let's multiply by, so we'll do a 16K transform. And now you can see that the shape of the function has actually changed, and we're sampling a different function. So there's two things, two effects taking place here. One is the zero padding effect. When you take a transform that's longer than your sequence, internally the data is being zero padded. Zero padding, as we have seen now, produces more samples of the same underlying function. If we want to change the resolution, I would say that the transforms of the 1024 point sequence is higher resolution. Resolution meaning that the width of this main lobe is narrower for the longer data segment than it is for the short data segment. So in the short data segment, our main lobe is quite wide, but for the long data segment, the main lobe is narrow. And so the width of that main lobe has to do with resolution and the ability to resolve things, or two frequencies that are closely spaced. But the zero padding only doesn't change the resolution. It just gives us more samples of the underlying function. If you want more resolution, you have to enlarge the amount of data in the transform, or put another way, use a longer window on the underlying data sequence. Alright, so I think that's all I wanted to say at this point about plotting the DFT. Remember, all of this stems from the fact that we have this relationship between the DFT and the DTFT. We have this relation between the two transforms, and that's what we've exploited here, along with the idea of aliasing to make properly scaled frequency transforms.